Hi student, welcome to chemistry class. My name is Odison Olalekan Adiola. This learning program is brought to you by Igata Virtual Learning. Today we are going to be looking at electronic configuration, and then we are going to be discussing what electronic configuration is, the types of configuration, or how to arrange elements in terms of electronic configuration. We are also going to be looking at the rules principles that guide this electronic configuration. Now, what is electronic configuration? The electronic configuration describes how electrons are distributed in the various atomic orbitals. It describes how electrons are distributed in the various atomic orbitals. It is also defined as the arrangement of electrons around the nucleus of an atom. Arrangement of electrons around the nucleus of an atom. You will observe that in a typical atom, you have the nucleus at the center of the atom, and then you have electrons revolving around it in a circular path or in an orbit. Now, these electrons are arranged in levels or in according to their energy level. So this topic will be focusing on how these electrons are arranged, and then how do we arrange them, and of course how do we calculate those arrangements. Now you will observe from this video, from these pictures rather, that we have the ground state electron configuration of hydrogen 1s1. Now this electronic configuration gives us three key information. You will observe that number one is showing us the energy, that is 1s. That one means that it's in energy level 1. It's also showing us the number of electrons in the orbital or subshell, which is also 1, the principal number 1. It's also showing us the angular momentum, which is s. That means it's in s orbital. That's L is equal to 0. We are going to know about this very soon. It's also showing us the spin of that electron, which is plus half, because it's facing up. So these are informations that electronic configuration will provide. Now quickly, let's look at two ways by which we can write electron configurations. Actually it's three ways, but for the purpose of this video we'll be focusing on two. We have the SPDF notation and orbital box notation. SPDF notation and orbital box notation. In SPDF, let's go back to the hydrogen that we were using the other time. SPDF notation, you have 1s that shows the value of the energy level. We have S1 shows the value of energy level, S showing the sub level. We can have SPDF, but this is showing us that this is S. And then of course we have 1 that is showing us number of electrons to be 1, and of course the atomic number of hydrogen is 1. In the orbital box, will show us for helium. Now atomic number is 2. The orbital box will show us how they are being arranged. You have the energy level, you have the sub level, you have the number of electrons. But in addition to this information, the orbital box will now show us how they spin. One is going up and the other is going down. The orbital box will show us that. So these are two major ways to write electron configuration. In electronic configuration for the sub level, because you have the principal level, which is KLMN, we'll go into that later on. We also have the one which is SPDF. Now, for the purpose of this lesson, we are looking at SPDF, like I've said. So SPDF is sharp, principal, diffuse, and fundamental. That's the meaning of SPDF notation. And then this is showing us how the orbiter, the s orbital, the p orbital, and the d orbital look like. The s orbital is spherical, the p orbital is dumbbell, the d orbital is double dumbbell, but the f orbital is complex, and that's why it's not here. So we have this is how it is: s spherical, p dumbbell, d double dumbbell, and f is complex. Those are the shape of the orbitals that we are trying to study. Okay, there are three major rules that governs how electrons are arranged, or the electronic configuration. You will observe that at the left hand side you will see oneness. If we are arranging them, we start with 1s, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p, and the likes. But we are still going to be looking at that very soon. But let's look at these three rules that governs this configuration. Now you have the Aufbau's principle. Now the Aufbau's principle says that electrons enter into the lowest energy orbitals first. The electrons enter into the lowest energy orbital first. What does it mean? That in writing configuration, you fill the lower energy level, and the lower energy level start from 1. So you start from energy level 1. When energy level 1 is full, you go to energy level 2, you go to energy level 3. That is all what Aufbau is talking about. Quickly look at the picture at the side of this. You will see that we are starting with 1s, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d. Why are we having 3d before 4s? 4s before 3d? It is because 3d is higher in energy than 4s. So in natural sense, when you are writing the electric configuration of an element having a d orbital, and that those are the transition elements between in between GO2 and GO3, they have the atomic number 21 to 30. That's the first transition series. When you talk about the scandium, the titanium, the vanadium, the chromium, the manganese, the iron, the cobalt, nickel, copper, and zinc, all these elements are they are d orbital elements. So when you're writing their configuration, the 4s comes before the 3d. So Aufbau saying that you fill the one with lower energy first. That's why they are starting with 1s, then you go to the one with the higher energy. Okay, another one is the Pauli's exclusion principle. The Pauli's exclusion principle states that an atomic orbital may have up to 2 electrons, and then it is full. Now, what does that mean? In a simple man language, is that when you are filling an orbital, they cannot face the same direction. One will face up, and the other must face down. So when orbitals are paired, one is facing down, the another is facing up. They cannot face the same direction in the same orbital box. Okay. Now, then the Ohm's rule of multiplicity. The Ohm's rule states that when you get to a degenerate orbital, you fill them up halfway first, then before you start pairing them on. Now, what does that mean? But let's look at what is a degenerate orbital. A degenerate orbital means that they have the same energy level. For instance, the 2p in a please take note that S has maximum of 2 electrons, P has maximum of 6 electrons, D has maximum of 10 electrons, and F has maximum of 14 electrons. Now, if you are dealing with 2p, for instance, like what we are doing here, 2p has maximum of 6, 2 in each box of the 2p. Now, 2p is a degenerate because they are in the same energy level as 2p. Now, what Ohms is trying to say therefore is that if you are filling them up, you fill them singly before you start pairing them. For instance, look at the orbital that we are talking about here. Carbon is atomic number 6, 1s2, 2s2, 2p2. So they are filled 1s2. You feed them all round 1s1, 2s1, 2s2, 1s2, 2s2. Now the 2p that you want to fill, you cannot take all the 2 electrons and put it in one box. You have to spread them first before you now begin to pair them again. If you look at nitrogen, which is 7 now, 1s2, 2s2, 2p3, 1s2, 2s2. Now your 2p, you cannot fill, you have to fill 1, 2, 3. When it's now remaining, you now come back to the first box of the 2p. You now fill it again. Now let's look at oxygen. Oxygen explains better. 1s2, 2s2, 2p4. In the case of oxygen, now you feed them singly. That means 1, 2, each of the box of the 2p. You feed them 1, 2, 3. Now it's remaining 1. You now go back to the first one and pair. So you fill singly before pairing for a degenerate orbital. Okay, so the D and L orbitals are also degenerate too. The D and S orbital, only the D and F, only S is not degenerate because the maximum number of electron S can contain is just 2, only 1 box. But for P, it is having three box inside, so it's degenerate. They are the same energy level. Okay, quickly let's look at let's combine the 3 rules together. You have hydrogen, helium, lithium, beryllium, and the likes. The configuration 1s1. The other one, if you check the Haber-Bosch principle, for instance, where we talk about filling the lower energy level first. Now you will observe that the 1s were filled first for helium and lithium. The 1s was filled for, you fill the one with lower energy level first before you go. You start with lower energy level. That's 1s. Now when it comes to Ohm's rule, we look at carbon. Now look at Ohm's rule again, where you are going to fill singly before pairing. You observe that in carbon they fill it singly before they start to what? Pair. So then we now look at Pauli's exclusion principle that talks about no 2 orbital can be in the same direction. That means the one must go up, one must go down. If you check the oxygen now, when they started filling, they fill singly. Now they have come to pair. In that pair, you observe that one is facing up and the other is facing down. That means they cannot be in 2. They cannot face the same direction. So this is just the explanation of the 3 principles. Okay, now quickly let's look at the steps in writing electronic configuration. The first step you are going to do when you want to write electronic configuration is to know the atomic number of that element. It is important. At least you have to know at least 1 to 30 as a minimum, but you can go more than that to know the electronic configuration, the atomic number. Of course, you know the atomic number is the number of proton or electron in the nucleus of an atom. For instance, magnesium has 12 proton and 12 electrons. For a neutral atom, it has 12 proton and 12 electrons. Okay, so the second thing, if you are writing for magnesium, for instance, is to draw the 9 box. Why are we drawing 9 box? The 9 box is to represent the first 3 energy levels: 1s, 2s, 2p, 3s, and 3p. Then why again? Why are you drawing the 3 energy level? Magnesium is what's it called? Is in period 3, and of course it will extend to the 3rd energy level. Please take note of that. it is important that you study your periodic table. Magnesium is in period 3, so that's why we are drawing up to the third energy level. So the value of the period that a particular atom is will also determine the energy level. So if it's in period 2, you just finish the writing in period 2. Okay, having said that, you draw the box like this, and then you start to fill. You add electron each to each box. 1s, 2, 1s, or you fill 1 1 1 1 1. Okay, you fill them 1 1 1 1 1. Now you are now left with if you fill 1 2 3 4 5 6 1, it will remain another 6 if you fill it like that. So you come back 1 2, another one. Now the first one that you feed are focusing on one direction. By the time you are going the second time, you are focusing this opposite direction. So you now have 1s2, 2s2, 2p6, and 3s2, and that is for magnesium. You now use that diagram to know the electronic configuration, to determine the electronic configuration. 1s2, 2s2, and 2p6. Okay. Now you can try the electronic configuration of various other elements. For instance, hydrogen is 1s2, helium is 1s2, 2s2, lithium is 1s2, 2s1, hydrogen is 1s1 rather, helium is 1s2, lithium is 1s2, 2s1, beryllium is 1s2, 2s2, and like. Ensure you try this up till the first 30 elements. Make sure you try and do it up to the first 30 elements. Then another last thing that you have to take note is that when you look at hydrogen, lithium, and potassium and sodium, you observe they have similarity. They are ending with 1. They are ending with 1, showing that they are in what? Group 1. Showing that they are in group 1. You observe here now. You see 1s1, 1s2, 2s1. They are ending with s. They are also ending with 1. That shows the valence electron. That's the electron at the atmosphere is 1. So that places them in group 1. Of course, which are also, since the heading is in S, it shows that they are X block elements. They are X block elements. Okay. The same applies to the noble gases. They are ending with 8 or 2. Helium is duplet, 1s2, but neon, argon, and krypton are ending with 2s2, 2p6. Now if you add them together, that's 8, because they are in the second energy level, third energy level, fourth energy level. So 8 8 8. So you have the octet and the duplet. Helium duplet, neon, argon, krypton are octet structure. That means they belong to group 8 of the periodic table. Okay. The same thing with the group 2, the alkaline earth metal. They are ending with 2. So you can take well to practice this in the sense that put them in orbital box notation. Each of these ones that we have that are here, put them in orbital box notation. Also determine their atomic number from here. Please practice that, and I'll be willing to look at your result. Okay, let's just do one of these question. We have which of the following electron configuration represent that of an atom in its ground state? The answer is D. Why? Because the valence electron here is 0. So it shows that when an atom is in ground state, it has 0 energy level, and then of course the ground state of an electron, the energy level which usually occupy is the lowest energy for that electron. So that's why the lowest energy for this electron is 0. So it's at its ground state. Okay. Another one which I will look at is a question in WAEC 2012. I ask you to write which ions has a different electron configuration. You observe that A has different. In A, for instance, chlorine has accepted one electron, and then it has become a 288. Oxygen has accepted 1, that's 28. Magnesium have lost 2, it now become 2. It was supposed to be 282, but it has lost 2, it becomes 28. Aluminum has lost 3 electrons. Instead of being 283, it's now 28. But chlorine has gained 1 electron. Instead of 287, it has become 288. So if you are writing it, you have 28 for oxygen, magnesium 28, aluminum 28. Only chlorine has 288 in the configuration. So the odd one there is chlorine. The answer is A. Okay, so this is how far we are going to go in this video. In the next video, we will continue with electronic configuration and how it relates to periodic table and other question. Thank you and God bless you.